It's time to take a look at cutting speeds, feeds, chip loads, etc. Also, we're going to be looking at the different types of milling cuts that we take. Climb milling, conventional cutting, you heard me talk about those earlier. More importantly though, the types of feeds and speeds that we are going to be showing you in the formulas have all been prepared by the automotive industry, Society for Automotive Engineers, the machinist, high production capabilities which will probably far exceed your expectations and what you may be able to achieve on a small vertical type milling machine like the Bridgeports and the Bridgeport knockoffs. We'll show you the right formulas to determine the correct cutting speeds, the feed rates, the chip loads, etc. But bear in mind, these are averages and examples for maximum production. And I strongly suggest that you back away from those a little bit. We want to make our machine last. I believe in giving the machine a little bit of TLC while working it pretty hard so it earns its keep. But by no means do we want to wear a machine out in 2 or 3 years because we're trying to max it out every time that we turn the on switch. Alright, let's take a few minutes and go over the different types of milling cuts and how they're performed. You can see here we're talking about climb milling. The cutter of the rotation of the cutter is counterclockwise and we are feeding the material this direction into the cutter. So as these cutting teeth come around, in essence they're climbing, walking over the top of the material. This is done in more of a horizontal mode. You can do it on the vertical mill as well, and this should be done only for finish cuts. If we were to take a real heavy cut in this fashion without having some type of restriction on the table feed, either by manual or by a power feed, this cutter would want to really keep advancing and sucking that material into itself, pulling the material from the jaw, from the work hole down that we may have on the table. A more appropriate cut for most of our roughing cuts is going to be a conventional cut. The cutter is rotating in a clockwise position and we're digging out as we work around this cutter each and every time. We're scooping that work material out as we go. The machine itself is resisting the advancement of the cutter. We can do a lot of roughing materials this way, and then we'll come back with a climb cut and take 10 or 15 thousandths and work our way over the top, producing a very smooth, uniform finish on the parts. Now let's go to the bottom of our diagram and take a look at the chip load. And this will give you a little bit better understanding, I think, of what's actually occurring. Each flute or tooth on the cutter is coming around and scalloping up that work or material as it's removing material from the base plate, if you will, that we're milling here. We want to maximize the revolutions per minute and the depth of feed and the feed rate that we achieve this to pull off the maximum amount of material without abusing our machine. As we look at this cutter, can anyone tell me what type of milling we're doing? Is it climb milling or is it conventional milling? For those of you that said conventional milling, you're catching up to speed. The cutter is coming along, scooping out this material as it's working its way along. If we were climb cutting, the cutter would be going in a counterclockwise position, walking over the top of the part. Alright, we only use that in a finish cut application. That pretty well covers the two types of milling cuts, conventional milling and climb milling. If we've lost you somewhere along the way, by all means, reach over and hit the rewind, review this section until you have a good understanding of these types of milling operations. Now, let's take a look at spindle speeds. For some of you, determining the proper spindle speeds may be a little confusing. It's actually very simple. But in order to determine the correct spindle speeds, we need to understand more about surface feet per minute. And that is the amount that that cutter rotates in a complete revolution. Let's take a look at a chart that is going to show us some of the different surface feed rates for different types of materials that we're likely to encounter in our machining course. Aluminum, using a high-speed steel end mill, would have a surface feet per minute rate of 3 to 800. Quite a gap. So we would again choose something in about the middle of, let's say, 5 to 600 surface feet per minute. If we were machining with uncoated carbide, that speed goes up considerably to 7 to 1400. I would choose middle of the road at, let's say, 1000. Now let's take a look at some different types of materials. A low carbon steel. High speed end mill, 60 to 100. Uncoated carbide, 250 to 350. In stainless steel, 2 and 300 series, we'd be looking at 30 to 80 with a high speed end mill and 100 to 250 with an uncoated carbide. Okay, these are the different standards that we will use when we begin to calculate the correct RPM for the type of material and the cutter that we will be using. Remember, when we're trying to determine the correct RPM of our cutter, that these numbers that we've shown you are in surface feet per minute. It's very important to remember this when we calculate the correct RPMs. Copies of this chart and others are available in your machinery handbook. Remember, these are averages that we want to use in order to determine the correct cutting speed. Variables will include types of material, heat treat of those specific materials. Now, let's take a look in some practical applications and determine the proper spindle speeds for different materials. We have a 1-inch diameter cutter that we're going to be working with, and if we can just visualize unraveling that cutter at a starting point and rotating it 1 complete revolution, or multiplying it by 3, that cutter in surface feet is going to lay out 3 inches. Okay, very important. So 1 revolution of the cutter is equivalent to 3 inches if we were to just unroll it based on its diameter. Now, number of revolutions to make a foot. We would have 4 revolutions equals 1 foot. It's important to understand that our 4 revolutions is not a figure we're going to work with. It helps us understand that 4 revolutions equals 1 surface foot of rotation of a 1-inch diameter cutter. Now let's take a look at the formula. RPM equals feet per minute divided by the tool diameter times 0.26. This is the basic formula that we're going to be working with. Now let's apply that formula. We're going to be machining mild steel using a high-speed cutter. The feed rate per minute is 60 to 80 surface feet per minute. So let's average that out and use 70 as our factor. We've got 70 feet per minute using a 1-inch diameter cutter times 0.26. So if we were to multiply those two, that comes out to 0.26. We are going to divide 0.26 into 70, and that's going to give us 269, which is going to be the number of RPM that we are going to be using for a 1-inch cutter machining mild steel. Now let's use another example. Let's machine mild steel using a carbide cutter. If we refer to our chart, the surface feet per minute suggested is 250 to 350 feet per minute. Let's average that out at 300 feet per minute for our formula. So in order to determine our RPM, we've got feet per minute, which we've established at 300 feet per minute. We're going to use the same 1-inch diameter cutter times 0.26, and we're going to divide that into 300. And that equals 1,153. So we would simply look on our milling machine and try and find the proper speed that's as close to that. If we have a speed selection that is 1,100 RPM, more than adequate for the task at hand. If we have one that's 1,200 or 1,250, that again should be pretty decent depending upon the type of alloy or material that we are machining. Remember, this is a guide. Practical application, listening to the machine, is also to be taken into consideration when determining the correct RPM. Now let's again take it a step farther with a different diameter cutter. A 3/8 diameter cutter, the decimal equivalent is 0.375. We're going to be machining that same piece of mild steel using a carbide cutter. If we refer to our chart again, we're going to average the feet per minute out at 300 feet per minute. So we have 300 feet per minute divided by 0.375 times 0.26. 0.375 times 0.26 equals 0.097. So we're going to divide 0.097 into 300. And that gives us an RPM rate of 3,092. All right, so again, we would look up on the mill whether we're using a variable speed machine, and it's important to note here that a variable speed machine usually has a higher RPM rate than a step pulley system. Does that mean that the step pulley system will not work for us? By no means. They've been using the step pulley systems long before anybody dreamed up the idea of a variable speed motor. So we would simply choose an RPM rate that is close to our 3,092 that is suggested by working our formula. Now, if RPM really turns your crank, let's take a look at what RPMs are required if we're machining a piece of aluminum, again using a carbide cutter, 3/8 of an inch in diameter. Consulting our chart shows us that for aluminum, we've got 1,000 feet per minute is the proper cutting speed that we need to determine. So we're going to multiply again 0.375 by 0.26, and we know from our example above that that is going to yield a factor of 0.097. Divide that into 1,000, and we have a whopping 10,309 RPM. Now, before you jump out of your chair and complain that your machine, variable speed or step pulley, is not capable of turning 10,309 RPMs, let's keep in mind what I said earlier. These are simply guidelines, and these guidelines are based on America's highest production rate. The automotive industry is a good example of this, where maximum production and huge machines are on the assembly line. We're dealing with a Bridgeport style machine or a knockoff that's weighing 12 to 1,500 pounds, whereas the types of machines that are being used in industry may weigh 3 or 4 times that, possess a 30 or 40 horsepower motor versus your 1 to 2 horsepower motor on your smaller mill. It's also important to note that we don't have to necessarily turn at these speeds either, that we can turn at a slower RPM with a slower feed rate and still achieve excellent results. You don't have to have the 20 or 30 horsepower machine in order to produce parts, have a good job or good business in industry. These are just examples based upon figures for maximum production. We've shown you these examples so you can grasp the relationship between cutter diameter, material, and RPM. It's very important that we understand this whole concept of what we're dealing with. We talked about different diameter cutters, the different materials that we're machining, and how they relate to RPMs. If we deal with a 1-inch cutter using mild steel, our RPM rate is 269 revolutions per minute. If we step down to aluminum with a smaller cutter, that RPM range goes up considerably. So again, we're trying to get you to grasp this relationship. Smaller diameter cutters turn faster. The different materials that we're dealing with have a different feet per minute rate. All of these things come together, allowing us to determine the approximate speed that we want to be able to turn that cutter for maximum performance. It's important that we understand these relationships that we've talked about. We've shown you different examples. If something is unclear, by all means, review it until it's firm in your head so we can deal and show these under practical application as we move forward. Now, let's take a look at a couple of other factors that we'll need to deal with. We've shown you how to properly determine the RPM rate for a given cutter diameter. Now, the next important thing we need to discuss is the proper feed rate, and that is the amount of material that we can remove with that cutter at that given RPM. When understanding feed rate, it's important to know that feed rate is stated in inches per minute. This is the amount of material that the cutter is going to advance through, or the amount of material that we push towards the cutter in 1 minute's time. Inches per minute equals the chip load, and we'll look at our chart in just a minute. times the number of teeth on the cutter, 2 flute, 4 flute, times the RPM. Remember, we showed you how to calculate the RPM, so you've got that in the basket now. Let's take a look at our chart and determine the proper chip load, and then we'll go back to the board and show you some examples on how to properly figure the feed rate. We're going to be machining low carbon or mild steel. We have a section for plain heavy-duty mills, plain mills that are light duty. In my opinion, the Bridgeport type mill falls under the light mill application. If we're to look closely, we have a chip load of 5 thousandths per tooth. Now let's take a look at aluminum and see how it applies to steel. Aluminum and its alloys on a light duty machine, we have double the chip load at 10 thousandths. So you can see aluminum, when we really want to push it to the max, we can machine twice as much as we can in steel. Now keep in mind, these are for roughing cuts with a high-speed steel. And again, these are just averages that we want to determine. We'll see that these particular applications, when we start machining, we're going to listen to the machine, watch the cutter, see how it is performing in the milling operation. So with that knowledge at hand, let's take a look at our example. We're going to be using a 3/8 diameter high-speed steel cutter that has 4 flutes. The material that we'll be machining is mild steel. In order to determine our RPM, which is part of the equation, we're going to refer back to our chart for mild steel. We've got 80 feet per minute. We're going to be using a 3/8 diameter cutter times 0.26 yields 800 RPM. All right, our chip load from our chart, remember, was 5 thousandths per tooth. The number of teeth in our cutter, we're using a 4-flute cutter, so we have 4 teeth. Our RPM is 800. So our feed rate in inches per minute equals 0.005 or 5 thousandths times the number of flutes or cutting edges, which is 4, times 800. If we're to multiply those out, we end up with 16 inches per minute as a feed rate. Many of you are going to be going, wow, that is a lot of material to remove. And you're right. Remember, these are averages for roughing material and maxing out the cutter. I would not suggest from the get-go trying to establish 16 inches per minute as a feed rate with that cover. I would suggest reducing that by approximately 50%. Get a feel for what the machine is doing, get a feel for how the cutter, the type of coolant, and again, the material that we are machining. If it machines just fine at a 50% reduction or at 8 inches, that's fine. We can push it a little bit harder on the next part that we're machining. It's very important that we don't overstress our machine. Bridgeport will last you a long time. I've been working with mine for over 20 years now, and the machine is still in excellent condition. The only thing that we're sacrificing by babying the machine is how quickly we're able to spit the parts out. When we're working with feed rate and our hand wheels, remember that each revolution of the hand wheel is 200 thousandths. So if we have a feed rate that we've established at 8 inches per minute, how many revolutions of the hand wheel do we need in that 1 minute's time? 200 thousandths per revolution times 5 gives us 1 inch. We've got 40 revolutions per minute. So you can see we're clipping along at a pretty good rate, even at 8 inches per minute, in order to feed that cutter through our given material. And that's what we want to establish, is a smooth, even rotation of the hand wheel as we advance the cutter into the workpiece. When we start machining aluminum and steel, we're going to give you different examples, and you can see and listen to the machine in order to determine that ideal feed rate based on cutter diameter, type of material, and specific chip load for the material being machined.